If everyone can hear, I've drawn positive measure from Zoom, so we can start. Apologies for the slight delay, everybody. Today is the day of the sun, and we have had a partial solar eclipse, so I believe, but we'll cloud that belief. But we're very glad to have a guest who will tell us a lot about variability of the sun and other sectors today, and I would like to invite Saskia Hecker to make a formal introduction.
Good afternoon. I would like to warmly welcome Sarbani Basu, who's standing here already. Sarbani has her PhD in 1993 in India, where she was originally from, and then moved on to do postdocs, and also turned to do work on the sun in Queen Mary and Westfield College in London, the Theoretical Astrophysics Center in Aarhus, and then moved on to the Institute for Advanced Studies in Princeton, before she accepted in 2000 an assistant professorship at Yale, and she has been at Yale since then. So she has been a full professor since 2005, and since 2021, so very recently, a William A. Landman Jr. professor. And also she has been the chair for the last 6 years at the Yale Department of Astronomy. And in 2018, Sarbani won the George Ellery Hill Prize of the Solar Physics Division of the American Astronomical Society. So Sarbani, very happy that you're here. And must say, Sarbani is in Heidelberg till the end of November. So if you have questions for her that you cannot address during this talk, then there may be other chances. So, Sarbani, welcome.
Thank you, Saskia. And thank you, everybody, for allowing me to speak on my pet subject, which is the sun. And what I'd like to do today is tell you about how the sun changes, and a few words about how changes in the sun can affect us, which is one of the reasons we study solar variability. Okay. Now, this is one of my favorite images from NASA and ESA. It is a snapshot of the sun in extreme ultraviolet, taken in spring of every year, from 1996 till 2020. It shows you two complete solar cycles, how the UV emission increased, decreased. So I don't know if, yeah, you can see my cursor. Increased again, decreased again, and now it has been steadily increasing. So clearly, the sun is changing. Okay. Now, most of the change is actually in the higher wavelengths. So the upper graph here shows the output from the sun or solar irradiance as a function of frequency during, this is, I think this is solar max. This is the ratio of solar max divided by solar minimum. Minimum is when the sun is quiet. Maximum is when we saw all that UV. And you can see most of the activity is actually in the shorter wavelengths. There is still a debate in the solar physics community whether the irradiance variation, so the irradiance is the solar energy that we see on Earth. And remember, the Earth is on the ecliptic. Unlike other stars, we are not seeing 4 pi emission. So there's a debate as to whether the irradiance variation, which is of the order of 0.1%, is actually a luminosity variation or not. But I'm not really going to address that. It goes on to, it sort of depends on how you define irradiance variation. What do you think causes it? So this is, again, one of my favorite pictures. I wanted to show it because this is a snapshot of the sun taken at the same time by the Solar Dynamics Observatory at different wavelengths. This is a Dopplergram, which is velocity, so don't worry about that at the moment. This is a magnetogram, which is solar magnetic fields. This is what we see on naked eye view. We'd see a simple spot here on the sun. But if you looked at different wavelengths, this wouldn't be a dark spot, but rather a bright upflow, a bright spot. So solar variability in that sense, at least the spectral variability, is quite complicated. Now, I have to show off, because this is possibly the most high resolution image of a sunspot, that's a dark spot in the sun caused by concentrated magnetic fields, taken to date. This was one of the first light images of the Daniel K. Inouye Solar Telescope, which is a new solar telescope on Haleakala on the island of Maui in Hawaii. The spatial resolution on the sun is about 70 kilometers. So we're really talking small distances on the sun. But this is, I just wanted to show you because it's a pretty picture. And also when we think of solar variability, we usually think of these sunspots, the number of sunspots increasing and decreasing, and increasing and decreasing and increasing and decreasing again. And this is a graph of the monthly averaged daily sunspot number from about middle of the 18th century to, when did I download this graph? Maybe a month ago. So you can see we are here. Solar cycle is increasing. The last solar cycle was pretty puny. The one before that was very active. We've had smaller solar cycles, we've had larger solar cycles. And this is what the eye sees as solar variability. And the sunspot, it's actually not just the sunspot numbers, but where you see the sunspots on the sun. At the beginning of each solar cycle, they start at sort of highish latitudes. And as time progresses, they go down in latitude. Each sunspot doesn't last more than maybe a solar rotation, maybe 2 solar rotations. So you see multiple sunspots come up. And for obvious reasons, we call this the butterfly diagram, because these are the wings of a butterfly. Okay? Now, the graph below is the same thing, but in magnetic fields. So this is a magnetogram. The yellow and blue are different polarities. And here what you can see is how the polarity of the fields change from one cycle to another. Look at the polar fields. In this cycle, it is yellow, so it's one polarity. Next cycle, it's blue, then yellow, then blue. So on top of the 11-ish year solar cycle, we have a roughly 22-year magnetic cycle. And one of the reasons we study this is sunspots can actually emit huge amounts of energy and huge amounts of particles. Sorry, let me see if I can play this movie. This is a movie of what's known as a coronal mass ejection. You'll see that mass ejection. If this hit the Earth, and if the magnetic fields were such that the Earth's magnetic field is disturbed, we could get a lot of issues here in terms of power lines, etc. So it could actually affect not so much life on Earth, but technology on Earth. In fact, the first indications of effect on society of these flares was the so-called Carrington event of 1859, when there was a huge flare. The highest technology thing at that time were telegraphs. And what people found is, A, the telegraph wires were overloaded, and even without batteries, you could send messages. So there was extra electric fields there. And the scary thing is, ice core samples have shown that the event was really, really strong, stronger than what we've seen anything recently. And if we have a Carrington-like event today, we could have trillions of dollars of damage. Okay? Now, just to scare you even more, there was even actually a threat of a nuclear war in 1967, which we didn't know till the 30-year moratorium on these information was lifted. There was this huge solar event, which caused NATO radars to be jammed in Greenland and elsewhere in the Northern Hemisphere. And of course, the first thing that came into the army's mind, the military's mind, is, oh, the Russians are preparing for an attack. They're the ones jamming a radar. Fortunately, by then, the US Air Force had its solar physics office, and they could persuade the powers that be, because warplanes had been scrambled by then to make sure they're ready for flight. But they could persuade the powers that be that, okay, it was a natural phenomenon. And since then, the Air Force, actually, the US Air Force has been supporting quite a bit of solar research. Yeah, well, it has its pluses and minuses, but it's money to study the sun. So this is what I was talking about. If we had a quarantine event today, it would affect things like your GPS. You know, GPS, your Google Maps, you use every time to navigate. Every time you do a credit card transaction, every time you place a call overseas, all of that is going to be affected. So, okay, so what is the problem? Because clearly there's an issue, which is why I'm talking about it. A, we cannot predict the events. We know that a stronger solar cycle with lots of sunspot means there'll be more events. But forget about being able to predict an event. We can't even predict how strong a solar cycle is going to be. We do not know enough. And to give you an example, this graph, so on this axis, you see the sunspot numbers, what is the predicted number of sunspot at the solar cycle maximum. For solar cycle 24, which had its maximum in 2015-ish. All these colored bars are different predictions, okay? So these dotted and the dashed lines are the median and the mean of the predictions. The actual strength was this blue line here. So the question is, did these predictions, which match the cycle, actually predict the cycle, or was it a chance prediction? We'll know with cycle 25 because there were fewer groups this time who were willing to actually predict the peak of the cycle. We'll have to wait, I think, another 2 or 3 years to know which of these is correct. So what can we do? Well, the solar cycle is something which is clearly emanating from inside the sun. So what we want to do is try and understand what is happening inside the sun. And not just through our 1D models. Yes, 1D models are good. In fact, I'll show you how good they are. But what are the changes on short time scales? Not on the millions and billions of time scales, which we actually understand quite well on which stars evolve, but 10 or 15 years over which these matter. So the way we find out what's happening inside the sun is through helioseismology, which is the study of solar oscillations. So I'm going to give you a 2-minute crash course in helioseismology. For those of you who've heard me before, please feel free to take a 2-minute nap. So the sun oscillates in millions of different modes. These are normal modes of the sun. So what do we mean by normal mode? You have a body in equilibrium, you disturb it, it'll oscillate, okay? The oscillations, thankfully for us, are linear and adiabatic. And I say thankfully for us because linear oscillations are easy to deal with. All observed modes are either acoustic modes, meaning sound waves, where the modes are basically the restoring forces pressure, or surface waves known as F modes. Once upon a time, F stood for fundamental, till helioseismologists started talking to classical pulsating people who study classical pulsators, and for them, the F mode is merely the lowest radial fundamental mode, which is not what we mean by F mode here. The F mode is a surface wave, the sort of waves you see on a lake or an ocean. And we characterize each mode by three numbers: the radial order, that is the number of nodes inside, which is n; the number of nodes on the circumference, which is L, the degree of the mode; and the number of modes on the equator, which is the azimuthal order n. The L and M are just spherical harmonics. So those of you who've had exposure to quantum mechanics, well, that's the hydrogen wave functions, angular eigenfunction. We use exactly the same thing. And just like a hydrogen atom, if we had a spherically symmetric system, then M's don't matter. Because to define M, you need an equator. In a spherically symmetric system, you can't define a unique equator. So all modes with the same L and N are degenerate and have the same frequency. If, on the other hand, you can lift the degeneracy, like rotation, that breaks spherical symmetry, your modes will split into 2L plus 1 modes, 2L plus 1 values of M. And 2L plus 1 values of M is a lot of modes. In the sun, we routinely use modes up to L of 250. So you are not going to fit 501 peaks in your power spectrum for each mode. Instead, what we do is we describe a given frequency with a given N, L, and M as a central frequency that depends only on N and L, and an expansion in polynomials which depend on M. They're functions of L, of course. And we basically use Clebsch-Gordon polynomials. And this A is the A coefficients, as we call it. Now, they're interesting because the central frequency depends only on the structure. The odd order A coefficients depend only on the rotation. It's a slow rotator, which is why I can say that. And the even order A coefficients depend on the second order effects of rotation, magnetic fields, any other asphericity you can think of, including distortion of the sun. But in the case of the sun, the difference between the radial and polar, the equatorial and polar radius, the ratio, the difference, is of the order of a few parts in 1 over a few parts in 10 to the 5 or something. So a few parts in 10 to the minus 5, or even lower. So for all purposes, the sun is actually a sphere. It's not spherically symmetric, but it's a sphere, which makes life easy. So we have lots of helioseismology data sets, but not enough. The longest is it's approaching 40 years, which is a small network called the Birmingham Oscillation Network Group. It's a ground-based network which only observes low-degree modes. Then there's the Global Oscillation Network Group, which has this network of 6 stations. MDI was an instrument on SOHO, which is no longer operating because HMI is MDI's big brother. So once HMI started giving a lot of data, MDI was switched off deliberately. Then there were other networks that existed for a time. So what do the data look like? I love to show this plot. So on the x-axis, you see the degree of the mode. The y-axis is the frequency. This is one of the usual data sets, a 72-day data, a set of frequencies from a 72-day time series. The reason we can do so well is this. These are 500 sigma error bars. Sorry, 5,000 sigma error bars. So our data are very, very precise, which allows us to do precision astronomy. So what have we learned so far? We've learned solar structure, we've learned about solar dynamics, we've learned a bit of physics, which I'm not going to talk about here. But what I am going to spend a little bit of time on are solar cycle related changes. Okay. So, but before that, what do we know from helioseismology about solar structure? What these two graphs show are the relative difference in sound speed between two models and the sun. And we do this with helioseismic inversions. What do I mean by inversions? Oscillation frequencies depend on the structure. So if we have enough oscillation frequencies, we can figure out the structure. Okay. What we can actually do is figure out the difference in structure between a model and the sun. And so this is the difference in structure. And what I'd like you to see is the scale here. Okay, even at maximum, this difference is 0.5%. In most fields of astrophysics, they'll say, oh, we solved the problem, let's go, that's zero difference. But clearly there are differences which we still don't completely understand. And the difference in the core is even smaller. And this is why in the mid-1990s, we had said quite loudly, the nuclear physicists wouldn't listen to us, the particle physicists, that the solar neutrino problem didn't rest with the sun because the models were fine. The solar neutrino problem is a now solved problem, which was basically the number of neutrinos detected were about a third of the number of neutrinos predicted. Turns out neutrinos change flavors because they're not massless particles. Now, structure, we understand. This is just a result of our simple equations of solar structure and evolution, okay? Problem is rotation. This is what was predicted. We have known from observations for years and years that the solar equator rotates faster than the polar regions. And using simple hydrodynamics, it was predicted that isorotation contours of the sun will be parallel to the solar rotation axis. What we see instead is this. You have the differential rotation at the surface continuing till roughly the base of the convection zone, and then solar rotation becomes solid body-like. At least as far as we can determine. We can't go very close to the core because we don't really have, our data doesn't have sensitivity. Now, I would like to show you this figure instead of showing a plot like this, where you can see that, yes, solar rotation increases and then changes nature, actually show plots at different latitudes as a function of radius. So that's the equator, that's 60 degrees, that's 75 degrees. And I would like you to see two regions, concentrate on two regions. That is what's known as the solar tachocline, the region where the differential rotation in the convection zone goes into a solid body rotation. That is what we call the near surface shear layer, where there's a small region, about 5% of the solar radius, where the rotation rate increases inside. We still don't know what causes these features. The near surface shear layer is some complicated interaction with Reynolds stresses and magnetic fields. The tachocline is still a bit of a mystery. Now, the tachocline is not coincident with the base of the convection zone. It's actually prolate in shape. So if I look at the central region of any of this change, the central region is in the radiative zone at the equator, in the convective zone at high latitudes. At 45 degrees, which is this blue curve, it's almost coincident with the base of the convection zone. Now, in stellar astrophysics, and particularly in the exoplanet community, there is this tendency to equate tachocline with the base of the convection zone. It really annoys me because even in the sun, the tachocline doesn't coincide with the base of the convection zone. And they're two separate things. The tachocline is a dynamical feature. The base of the convection zone is a structural feature that depends on the thermodynamics. They may be correlated, but they may not be. And we know that the tachocline, as I'll show, changes as the solar cycle changes. Okay, The near surface shear layer, it's a region where, as a function of latitude, the logarithmic gradient of the rotation rate is actually a constant. And again, we don't understand the near surface shear layer. Then there are zonal flows, which are, think of bands of Jupiter. So we have the rotation rate of the sun, which is an average 2 kilometers per second. You subtract the average rotation rate of a solar cycle from rotation rate at each epoch, and you'll see prograde and retrograde bands. Those have the order of 10 to 15 meters per second. We call them zonal flows. And I'll give the plot away right now. They change with solar cycle. Then there are these flows from the equator to the poles. We call them meridional flows because they're in each meridian. They also change with solar cycle. This is just showing the average, a 4-year average meridional flow. And again, at maximum, it's about 15 to 20 meters per second. So these are small velocities, so it's been really hard to tease them. And then there are these swirly structures near the poles, which are about 0.5 meter per second, last a couple of rotations. The reason there's this big gap in the middle is we are not sensitive to the polar regions. We are observing from the ecliptic, so we can't really see Doppler measurements at the pole. We need a mission that takes observations from the pole. And recently there have been reports of finding inertial modes on the sun, so Rossby waves, the way we find in our jet stream here. So in other words, there's a lot of dynamics. Fine. Why do we care? Because they change with solar cycle. Okay. Now, we knew since the 1990s that solar frequencies changed with solar activity. What we know now is that the change in frequency depends on the range of frequencies. Now, normally, if you think of the sun, people will say, oh, the sun oscillates with a period of about 5 minutes. So that's 3 millihertz, but that's about. You can see modes as low as, I think the lowest, most authoritative discovery, I would say, or detection, something like 900 microhertz. The highest we've seen up to 6,000 microhertz. So the frequency range determines how frequencies change. And I'd like to explain this graph to you. The black points are the change in frequency that you get when you subtract an average frequency out for different frequency ranges. The red and blue are measures of solar activity, of surface solar activity. Now, in these two cycles, you can see that the high frequencies, they sort of follow the solar activity, but the low frequency does not. This is the same thing, but a smooth version of the curve. So clearly, again, it's not a one-to-one relation. And again, it's not something, I'll repeat this often in this talk, we understand. Okay. Now the splitting coefficients, which tell us about rotation, they also change. So the background blue is the sunspot number. The colored points are splitting coefficients. The 3 colors are from 3 different instruments. So you can see some sort of there's a systematic difference between 2 instruments, but that's okay. We can handle that. But as you can see, different coefficients, the different Krebs-Gordon coefficients have different dependencies on the solar cycle. Why? So what does it actually tell us? One thing, if you just look at the latitudinally independent component of solar rotation, that has been changing, by about 0.5 nanohertz over the solar cycle. So you can see 2 solar cycles, 2 maxima. Now, if you're worried about things like angular momentum conservation, don't, because these are the very outer layers of the sun, which have very, very little mass. And we think most of the energy and angular momentum then goes into the magnetic fields. We're not talking much mass here. So by the time you're at the base of the convection zone, you don't see much change. This is the same thing, but plotted against a proxy of solar activity. So you can see that as solar activity increases, the rotation rate increases, but then seems to saturate. So red is the ground-based observatory and the blue are a space-based one. So they agree in that sense. Now, the average rotation rate between solar cycles change, and this is the change. We're talking about rotation velocity here, not rotation rate, okay? But this doesn't tell you much. It's not very pretty. And what does this change even mean? To actually see the change, what we do is take the rotation rate at each epoch and then subtract out the average rotation rate. Oops. So this is what you see, but then what we do is plot it for a given radius as a function of time and latitude. And what you see clearly then, red are prograde flows that start at mid-latitudes and move towards the equator as solar cycle increases. So these lines, vertical black lines, are solar maxima. The white lines are solar minima. So we have 2 and a bit solar cycles data here. And if you plot the positions of sunspots, these are these black points that you see, they lie at the interface between this prograde and retrograde mode. We also see these flows going towards the pole, and this is where cycle 23 and cycle 24 differ. Look at the polar structure of the flows, they're very different. And in cycle 25, we don't even see that yet. So, bit of an issue. Yeah. Now, this is the same thing, but now I've plotted these retrograde and prograde, again, same colors, prograde red, retrograde green, as a function of depth for various latitudes. This brown line is the base of the convection zone. Don't believe things this deep, the error bars are large. But what you can see is, for the prograde pattern, the leading edge starts around the solar minimum and reaches the surface at the solar maximum. Here too, at the next cycle too, it started around the solar minimum and reached the surface at the maximum. So the pattern is predicting the solar cycle. In other words, we know at solar minimum, if we have the data, whether we're going to have a solar cycle or not. Now, how these lead to sunspots is something we still don't know. It's supposed to be some sort of Lorentz forces playing around and reacting with the flows. I'm going to skip this because it doesn't matter, but I talked about meridional flows changing. These are the flows from the equator to the pole in both hemispheres. Now, meridional flows are considered very important these days because current solar dynamo theories actually rely on meridional flows, taking magnetic flux from the equatorial regions to the polar regions to start to recycle the magnetic fields for the next cycle. And again, these are the changes that you see in the flows. They're not large, but they're there. And they too seem to follow a butterfly-like diagram. And the reason this figure looks so strange is because of the data that were available. So this is the era where we only had high spatial resolution data for 2 months or 3 months a year. This is when the GONG ground-based mission started taking high resolution data so we could get continuous data. This is the era of the helioseismic and magnetic imager on SDO, where we are getting a high resolution image every 4 to 5 seconds. So we actually can do the data. Okay, so we're still trying to figure out what's going on. About the tachocline. So this is a schematic of the tachocline, okay? So you have the equatorial rate, which changes suddenly. You have at every other latitude. So what we want to do is figure out if this change in the rotation rate changes. The reason tachocline had caught people's attention is this is at the interface of the convective and the radiative zone in the sun, which means you could be, so it's also a shear layer, so you could produce strong magnetic fields and maybe even store them. Newer dynamo theories don't rely completely on the tachocline, but the fact is we still cannot understand it. No, as far as I'm aware, none of the MHD simulations, global MHD simulations that are done to try and explain solar rotation rate and magnetic field generation can produce the tachocline from first principles yet. If you put a tachocline by hand, you can strengthen it, but if you don't have a tachocline, you can't reproduce it. But this quantity, this change in the rotation rate, I call it the jump, that changes with solar cycle, and this is what we see. So the gray curve in the background is just the sunspot number to show you solar maximum, minimum, maximum, minimum. At the equator, this is the pattern. These are the patterns at 15 and 45 degrees, and definitely it's not an 11-year cycle. The other interesting thing is, so I'm hoping maybe it's a 22-year cycle, we'll know. So this bit is new analysis with cycle 25 data, but we are nowhere near the maximum yet. Now, this is the same thing, but plotted against, a proxy of solar activity. So the higher this number, which is the flux at 10 to 10.7 a centimeter, it's a radio frequency flux. Now, if we plot this as a function of the magnetic field strength, and we color code them by whether it's the increasing part of a cycle or a decreasing part of a cycle, what we see is a hysteresis type loop. So if we look at the red points, that's this part of the solar cycle. Okay. The brown points are this lowering part of the solar cycle. Okay. The blue points are this, and the purple points are this, and the light blue points are this. So you can see that the brown and the red do not follow the same path on this curve. And also at the same value of the solar flux, the brown and the red and the purple and the blue show different amounts of that jump. Just telling you again that this is not a single sunspot, a single solar cycle dependence. So these light blue points are the new solar cycle, and they seem to be following more or less the cycle 24. So I'm wondering if this will go up, go down, and then maybe it'll go up and go down the following cycle, but by then I'll probably retired from the field. Who knows? Yeah, you need a lot of patience to do solar cycle related changes. Okay. Now, this is the change at the 30-degree latitude. I hadn't plotted it with the others because the change in the rotation rate is very small. You can see it's of the order of 1.5 nanohertz. But this one is completely anti-correlated. At 30 degrees, it's completely anti-correlated with the solar cycle. Almost completely. There's a slight time shift. Okay. Changes in structure? Well, it's very difficult. You can change solar frequencies, only if the magnetic pressure is a reasonable fraction of the gas pressure. And solar density gets pretty high pretty quickly as you go inside. Now, the tachocline is at the convection zone base, and given the older hypotheses that that is where you build up your solar dynamo, people thought that we'd see a change there. We tried very hard. We did manage to see something, but is that a change? Maybe. This is the difference in sound speed between solar minimum and maximum. And we could do this only because we had a whole solar cycle, almost a whole solar cycle of data. We did a PCA analysis and found, okay, so you can sort of believe the results where the blue line and the red points match. And the two panels are two different data sets. But during the COVID years, when I was quite sick of sitting at home and working, I decided, let's try something. When we were doing this work, we decided we wanted to keep the usual spatial resolution. I said, oh, let's forget about spatial resolution. Because the better your spatial resolution is, the less precise your results are, because that's a trade-off. I said, okay, let's forget about spatial resolution. Let's make our resolution kernels very wide, but to get the errors small. If we do that, indeed, you can see a nice change. And I don't think anybody will disagree that there is some sort of a change here. This is against time. This is against the solar magnetic fields. So yes, there's some change, but you can see it's tiny. It's very, very small. So the biggest changes we see are in solar dynamics, and we don't really understand that completely. So what does all this mean? Okay. And all we have are questions. We have 2 full solar cycles worth of good data, and we have a few more years of solar cycle 25. We can see the changes, but we haven't quite yet been able to tie the observations to a physical theory. It's also, we are facing challenges because of the cycle-to-cycle differences. Now, solar structure can be explained quite easily by the equations of stellar structure and evolution, which is why when I showed you the inversion result for solar structure in the beginning, our models did very well, but internal rotation is still difficult to reproduce. There are some people, Steve Balbus, I think, who has a hypothesis that under assumption of thermal wind balance in the solar convection zone, you can reproduce the differential rotation in the convection zone, but it's not completely clear if there is a thermal wind balance in the convection zone. The near surface shear layer is the other big mystery. You might be able to reproduce it in the lower latitudes by interaction of Reynolds stresses, which means you have to have a fully compressible simulation just to get it. But even then, you can't get it at the higher latitudes. The tachocline is still a mystery. So the question is, what do we need to solve these issues? More observations, of course, it's a given, particularly given that there are cycle-to-cycle differences. Better observations, in that case, what do we need? Do we want to study the solar poles? Because, I mean, many of you must have seen the Juno images of Jupiter poles with, the beautiful, the whirlpools around the pole. We don't know if there's anything like that on the solar poles. We would need a mission, a helioseismology mission, to be very high off the ecliptic to actually see that. So maybe that'll tell us something. And of course, we still have to learn how to do better analysis. Our data are so good that I think we haven't tried our best to eke out all possible information from the data that we have. So So thank you all for your attention. I'll be happy to take questions.
Thank you very much, Sarbani. That was so impressive, the position that you can measure these things, and it's sort of tantalizing from being in the audience just to see, you know, what does it mean. I'm sure that we will have lots of questions.
We know that the conversion kernels have a finite spatial resolution. Can we tell what the thickness of the real plans is? It consistent with the discontinuity or?
It is, so the way we deal with the tachycline at the moment is through a forward modeling. We don't do an inversion. We try to fit models so that the resolution is less of an issue, though I have colleagues who are trying to use clever inversion techniques to actually resolve the tachycline, but they aren't quite there yet. But I can actually, I had a figure, but I glossed over it about the thickness of the tachycline. Oops, sorry, I went too far. No, not far enough. Yes. So at the bottom, I show the PDFs of the thickness of the tachycline for two models. One is a simple sigmoid fitted to this part of the tachycline, and another is an integral of an error function. So it's another sigmoid-like curve. There is a difference in definition of the two thicknesses, but the way I've plotted it, I've converted both of them. So the solid line is the sigmoid, and the dot dashed is the error function. And you can see at the equator, it is almost consistent with the discontinuity. But at higher latitudes, it's maybe a tenth of a solar radius thick. I'm trying very hard to figure out if the width changes with solar cycle, because there are dynamo theories that predict the width changing. But you can see that from the PDFs that the PDFs are pretty wide, so you know, seeing a width change is going to be tough. And we're in a bit of a bind here because if you want precise results, you want a longer time series, but if you have a longer time series, you are averaging over solar cycle changes. So yeah, it's tough. But it doesn't look like a discontinuity except very close to the equator. And I wouldn't quite believe the equator anymore, because paradoxically, when we look at helioseismic modes, they don't have too much. They have sensitivity at the equator, but it's a bit difficult to deal with. So just slightly off the equator, we are fine. So 5 degrees is okay. 0 degrees can be a bit difficult, but yeah.
When speaking about the absence of variations on the tachycline, there would be 22 year tachycline, 22 tachycline. This comment on whether it seems to all of the variables or do we expect the general variation?
Could you please repeat the question? I'm not sure I completely understood it. Are you asking?
You suggested that it would be not
11 years.
But 22 years for the tachycline. And now theory allowing.
There is no theory for the change. I mean, no, that's not correct. There are theories which talk about the change in the tachycline, but in general terms. Like if the magnetic field configuration is sudden touch, we would expect the shape to change, the thickness to change. I am yet to see an investigation that actually talks about the time scale.
But making sure magnetic field up and magnetic field down, it seems like the same dynamic.
The same, sorry?
The same age from the dynamic point of view. And still it could make and change in the force in which.
Yes, definitely. And which is probably why we have this hysteresis-like loop. I mean, we have to explain why these don't fall on the same path. That is probably magnetic field. It's the usual magnetic hysteresis. But what is more difficult to understand is why are these blue and purple points at a different place than the red and brown? The blue and purple are a different solar cycle than the red and brown. But at the same value of the global magnetic field, they have different results. So something is different at the tachocline. So yeah, lots of interesting problems, no solutions yet.
I actually had a sort of question myself. And I've read papers about the fact that the sun will capture dark matter particles. And I wondered if that was like any role of view. Because you have scattering events in the middle, which will take energy in large steps.
Yes.
Further out.
So there are, there are actually a few papers which deal with dark matter in the core and whether we see what effect we see of it. But the fact is, and you can only put upper limits, because standard models are so close to the sun. So there's very little room to play with.
Right, I'm thinking about the temporal deviation, you know, because, you know, there are some dark matter models which have a structure, right? So,
Yeah.
especially when this and things like that.
So would there be, okay, so I know nothing about that, but my question then would be to you, are those captured events dependent on the solar magnetic field? Because if they are, then you could play a role, maybe you could think of something.
Yeah, but you're going way beyond conception. No, yeah, well, I think the second order effect.
Yeah, exactly.
No, I find it fascinating. I've read papers actually about planets having their solar quantum change.
Yes.
Using the effects, you know. But anyway, thank you very much for that. You've made it completely,
It's really, it's not a crazy idea. It's an idea which you have to deal with given the current instruments. So one of the things that happened in the early days of helioseismology, people said, okay, we have these very, very precise oscillation frequencies. Let's figure out if we can measure the value of the gravitational constant.
wow.
You know, all you have to do is change the value of the gravitational constant and see how your models change. The problem is we may not know G very well. We know to 5 place of the something. We don't know the mass of the sun, but we know G times n sun to 14 or 15 decimal places. And that's what comes in the oscillation equations, G times n.
Okay.
So you can put very strict limits on G. But to do that, you have to remember if you change G, you have to change n sun, so the G times n sun. What has been done, however, is to put limits on G dot, because there have been cosmological theories that claim that the gravitational constant changes with time. Because we know G times n sun today, but we don't know G times n sun when the sun was off. There have actually been quite a few, I can think of at least 3 or 4 attempts to do that. And each of them have given an upper limit to the change, which is tiny. So 1 over G dg by dt is less than 5 times 10 to the minus 12 or something. Yeah. Small changes.
I'm just trying to work out how many solar cycles there are
No, but you don't need the solar cycle to do that. All you're doing is looking at the structure. So if you want to look at changes in G dot, what you do is change G dot. I mean, have a model of G dot. evolve a solar model to present day and check its structure against the structure of the sun. That will give you, tell you if your G dot is too high, too low, or just right.
Well, it's really fascinating, I mean, that's the, as you said, it's vision.
It's specific.
It's specific. Doing that. Well, I don't see more questions in the hall, so I think, we'll gradually wrap up. So, thank you very much, Sarbani. That was a real privilege to be here today, and it was a very fascinating insight to the science of the laboratory, and you know, that was a really mind-blowing what you and the laboratory have been doing. Thank you so much.
Thank you. It's been an incredible 20-something years doing this.